Improper integrals are a type of integral where something about them is not quite right or doesn't quite make sense. Well, it does, but you'll see what I mean. There are really two types that we're going to take a look at here. One is going to have what's called improper bounds, and the second is going to be the argument does not exist everywhere in the interval. Okay, so what do both of these mean? How do you have improper bounds? Let's start out with a very, very simple question. What if I said, what's the integral from 1 to infinity of 1 over x dx? So a very simple integral. But my bound is at infinity. How do you plug in an infinity there? So the idea is, since infinity is not an exact value, that means that bound is improper. So the only thing that makes this integral improper is the infinity, because 1 over x exists for all the values from 1 to infinity. Now, if it didn't exist in that interval, it would also fall into this second case, right, where the argument doesn't exist on that interval there. But this one does exist. So how do we handle an improper bound? Well, it's pretty simple. Let's do this. Since we can only plug in numbers, let's call that top value a number, and I believe most textbooks, I don't know why here, use a b. So let's say that it is a number, but then we want to see what happens as that number heads towards that bound. So in this case, we're going to replace our infinity with a number or a value b, and then we're going to let that value head off towards infinity. So let's see what happens here. We go ahead and integrate like we always would. So the integral of 1 over x is the natural log absolute value of x. We want to evaluate that from 1 to b. So it's the limit as b goes to infinity, the natural log of the absolute value of b minus the natural log absolute value of 1. All right, now I can get rid of these absolute values if I want, because I know both the 1 and the b are positive because we're heading out to positive infinity, but that's okay. We'll leave it there for a second. Now I know just by a fact that the natural log of 1 is a 0, so this here is 0. So the real question is what is the limit as b goes to infinity of the natural log of b? Well, again, this is one of those cases where if you know what the picture of the graph looks like, it's really going to help you. The natural log of x, or any value, looks like this. We have a vertical asymptote at x equals 0, because we're never allowed to take the log of 0, and the graph kind of looks like this. So as we head out towards infinity here, what's the graph doing? Now it's going up really, really slow, but it is always heading up, which means that's heading towards infinity. Okay, so we get an answer here of infinity. Now this brings us into a little bit of new terminology when we're talking about integrals. When we're talking about an integral from a to b, generally we're talking about area beneath the curve, or between the curve and the x-axis to be more specific. So here we're talking about area, which means here we have an infinite amount of area. When we say that an integral goes to infinity, we say that it diverges away from any physical answer, or another way to say that it does not converge to an answer. So a couple quick things. If you have an integral equal infinity, we say that it diverges, and if we have an integral equaling a number, we say it converges. Okay, so we'll see this terminology actually pop up a little bit more when we're talking about sequences and series. But here, if you're doing a definite integral, it has bounds, and for some reason it adds up to infinity, that means it diverges, and if it adds up to a number, it means it converges. So in this case, if you kind of wanted to see what the concept here was, here we have the curve 1 over x, at least this side of it, right? And we're integrating from 1 out there out to infinity. So we're saying how much area is beneath that curve. And it seems to make sense, right? Since this curve never touches the the x-axis, that there should be an infinite amount of area under that curve. So that kind of makes sense. Let's do something that kind of doesn't then. What if I change this problem just slightly and I say, let's take a look at the integral from 1 to infinity of 1 over x squared. So almost the exact same problem. Well, again, we look at this and you say, hey, I have an infinite bound there that makes this an improper integral, which means I want to turn that bound into a limit. So I'm going to do the limit as b goes to infinity, integral from 1 to b. I'm going to write that as x to the negative 2 right now. We integrate that, so it's the limit as b goes to infinity. What do? We bring add 1 to the power, divide by the power. Excuse me. When we add 1 to the power, we get negative 1 divided by that, so we get negative 1 over x evaluated from 1 to b. Okay, so top endpoint minus bottom endpoint. Let's see what happens. We get the limit as b goes to infinity, negative 1 over b minus, that's top endpoint, minus negative 1 over 1. So this is the limit as b goes to infinity, negative 1 over b plus 1. All right, so what happens to this value as b goes to infinity? Well, as b gets bigger and bigger and bigger, 1 over b gets smaller and smaller and smaller. So this value here is heading off towards 0, which means this value is 1. Now, if you're saying, okay, I'm good with that, here's where your intuition may really make a mistake. Remember, this was a graph of what 1 over x looks like. Well, on this side, 1 over x squared looks almost exactly the same. It's just a little bit, it actually comes on that side over here, kind of like this, and right there, kind of just comes in and it's a little bit lower. But it still's got the same idea, right? It heads down towards the x-axis but never touches it. Now the difference is, that little bit of difference between those two curves, one has an infinite amount of area underneath it, the other one only has an area of 1. So a little bit counterintuitive because the curves look so similar to each other. If you were to just graph them side by side, you probably couldn't even tell the difference between the two. All right, so since this one added up to infinity, we would say this first integral diverges, but since this integral adds up to a positive value, it converges. By the way, every integral you've ever done with bounds on it that added up to a number, it converged. All right, let's take a look at a slightly different type of improper integral. Let's say we have something like, I don't know, how about 0 to 2, 1 over x cubed, or x to any power. All right, now when you're looking at this, you'd be pretty good to say, oh, there's nothing wrong with that. Those bounds look fine, right? We got a 0 and a 2. And the bounds are actually fine here. The problem is, this function does not exist all the way from 0 to 2, right? This function does not exist at 0, which actually makes this bound of 0 improper. So to fix this, we're going to do the same thing that we did over here. We're going to turn that bound into a limit. So here I'm going to do the limit, and let me go ahead and put a b down there too, as b approaches 0. Now here's where it might get a little bit tricky. You got to think about this. We're only integrating from 0 to 2. So if we're looking at our curve, we are going from 0 to 2. Since we only exist in this interval, I can only approach 0 from above. So it's not the full limit, it's only a one-sided limit here. So we're approaching 0 from above, and I'm going to go ahead and write that as x to negative 3 since I have to integrate it. All right, so let's see what happens when we integrate this mess. We get the limit as b heads to 0 from above. Add 1 to the power, divide by the power. So that's going to be negative 1 over 2x squared. And we want to evaluate that from b to 2. Top endpoint minus bottom endpoint, what do we end up with? Well, I get the limit as b goes to 0 from above. Negative 1 over, let's see, 2 times 2 squared is going to be 8, minus negative 1 over 2 times b squared. So this is the limit as b goes to 0 from above, negative 1/8 plus 1 over 2b squared. All right, so what is this limit? Well, now we're approaching 0 from above, so value's bigger than b, or bigger than 0. When we plug that in, that's going to be something bigger than 0, but really small squared. So this denominator is heading towards 0, positive 0. 1 over 0 would be means this here is heading towards an infinity. So really what we end up with here is negative 1/8 plus infinity. Well, infinity minus an eighth is still infinity, so this is infinity. Which means that this original integral diverges. So in this case, here we had a bound where the function did not exist at. Now, I'm going to take a look at this real quick. Another way that you could run into this, what if we had the exact same integral? Let's say, but I'm going to change the bound slightly. Now these are the ones that most of us make an easy mistake on. You'd say, okay, look, the bounds are fine, the function looks normal, let's just go ahead and integrate. We get our negative 1 over 2x squared, top endpoint minus bottom endpoint. You'd actually get a number out of this and everything would look like it's fine, but you would be wrong. The reason is inside our interval here, from negative 1 to 2, the function does not exist. So what you need to do in this case, this is one of those, again, like this, that it does not exist in the region. You got to break this up into two integrals. We'd have to integrate from negative 1 to 0. Then we'd have to integrate from 0 to 2. Now for each one of these, now I'm going to go ahead and set this up. We would do the limit as b heads to 0. Now notice from below this time, negative 1 to b 1 over x cubed dx. And then I'm going to use a different letter over here. Let's do c heads towards 0 from above, c to 2, 1 over x cubed dx. All right, so basically we'd have to break it into two problems at that troubled spot and see what happens there. Now I'm going to skip a really quick step, because if you notice this integral right here is an integral that we already know, and we know that that diverges, right? So we know that this diverges, so the whole problem is going to diverge. Okay, so in this case, we can kind of stop right there just to save us a little bit of work. Okay, so if you have either an endpoint where the function does not exist or a value in the middle where the function does not exist, you have to take care of that by setting up a limit or breaking it up at that singularity point and doing a limit for each one of those. All right, let's take a look at another type that we might run into, or you absolutely will run into. Let's go back to where it's easy to see a bound and maybe a problem. What if I said the integral from 0 to infinity x squared e to the negative x? All right, so nothing looks particularly awful about this. The function looks okay. That exists everywhere, so we don't have to worry about that. But we do have this infinity as a bound. The way that we handled that is we said, okay, let's let that be a value that goes to infinity, x squared e to the negative x dx. All right, now for this integral, remember this integral is a biparts integral, and if you wanted to, you could actually use our tabular method for this, which I'm going to just to save us some time. Remember how this works. We have a sign column, a derivative column, and an integration column. The sign column starts with plus and alternates all the way down. The function you're going to take the derivative, it was x squared. You put in that column, you go all the way down till you get to a 0. The function you're going to integrate goes in the last column, and you continually integrate till you get down to the 0. Okay, so let me go back over here. This is going to be the limit as b goes to infinity. Now remember, to evaluate this, we go across and down. So our first one's going to be negative x squared e to the negative x. Then we go across and down. So it's going to be negative 2x e to the negative x. Then we go across and down. So that's going to be negative 2e to the negative x. And everything after that would be 0, right? Because we would get zeros for the rest of that. All right, so that was the integration. Just a reminder of by parts. So top endpoint minus bottom endpoint, we get the limit as b goes to infinity. That's negative b squared e to the negative b minus 2b e to the negative b minus 2e to the negative b minus, let me put some parentheses here. All right, when we plug in 0, so that's going to be 0 times something, so that's 0. 0 times something, that's 0, so this is going to be negative 2e to the 0, which is going to give us a 1. So this is the limit as b goes to infinity. Just going to clean this up a little bit. Negative b squared e to the negative b, 2b e to the negative b, 2e to the negative b plus 2. All right, so now we need to do the limit as b goes to infinity. So let's take a look at this one. I'm just going to bring this over to the side real quick. Give some room. There's our scratch work gone. So what is the limit as b goes to infinity of negative b squared e to the negative b? All right, if we do direct substitution, that would be negative infinity squared, so that's going to be negative infinity, times e to the negative infinity. Remember, that's 1 over e to the infinity, so that's going to be 0. Well, that falls into the case of L'Hopital's rule that we've seen in the past. So to do L'Hopital's rule, if we have 0 times an infinity, we bring one of them to the bottom. Well, since this already has a negative exponent, I'm going to just go ahead and move that to the bottom. It gives me negative b squared over e to the b. So all I did was rewrite it. Now if we try direct substitution, that's going to be negative infinity over positive infinity. That is one of the indeterminate forms that we can use L'Hopital's rule on. So I'm going to say this limit is equal, by L'Hopital's rule, the limit as b goes to infinity, the derivative of the top, negative 2b, over the derivative of the bottom. And I can't simplify that, so let's do direct substitution. We get, well, negative infinity over infinity. So, L'Hopital's rule again. This is equal, by L'Hopital's rule, the limit as b goes to infinity, negative 2 over e to the b, that's negative 2 over infinity, which is 0. All right, so a bit of side work there just to get this one thing right here. We know the limit as b goes to infinity of this first term is, that's 0. Well, here's the good news. It works out like this a lot, especially with polynomials and exponentials. What's this next limit? Well, notice this is negative 2b over e to the b. That's exactly what this limit is here. We know that that limit is also 0. And the negative 2e to the b, well, oddly enough, that's exactly what this limit right there is. That is also 0. So, this is just 2. Okay, so since we're going to be dealing with bounds that are at infinity and we're doing limits at infinity, you should guess that L'Hopital's rule is probably going to come into play quite a bit. All right, one more question we need to answer. Let's go actually back over here. One of the first two problems that we looked at in this lecture were these two integrals. We saw the integral from 1 to infinity of 1 over x dx was infinity, and the integral from 1 to infinity of 1 over x squared dx was 1. So this brings up a very good question. Here the exponent in the denominator is 1. Here the exponent in the denominator is 2. When it was 1, it added up to infinity or diverged. When it was 2, it added up to 1 or converged. It should make sense then that there should be a value between 0 or 1 That's the tipping point where it goes from converging to diverging, or diverging to converging, either way you want to look at it. So my question is, if I have the integral from 1 to infinity and I have 1 over to a power, most books use p here, for what powers, or for what values of p does this converge? Okay, so I hope everybody gets the idea, right? When it was 1, it was added up to infinity, but when it was 2, it adds up to 1, which means there should be a spot somewhere in the middle. That's where it changes from converging to diverging, or diverging to converging, depending on which way you're looking at it. Well, here's the good news. We're going to do exactly what we've been doing. Nothing's going to change, except we're going to have this value p floating around that we're going to mess with. So we're going to change this to a limit. Do the limit as b goes to infinity, 1 to b, x to the negative p dx, right? Because p is just a number here. By the way, for this case, as of right now, when you go and throw it up here just as a reminder, we're going to go ahead and assume, at least the way that we have it written for right now, that our p is greater than 0. All right, because I want to think about that as it's a positive number, basically. Okay, so if I plug that in, as I write it up there, let's go ahead and integrate this. So this is the limit as b goes to infinity. How do we integrate this? Well, that's going to be add 1 to the power, so that's negative p plus 1, divide by that, negative p plus 1, and we want to evaluate that from 0 to b. I'm going to just rewrite that just a little bit. This is the limit as b goes to infinity. I'm going to go ahead and write that as 1 minus p. You'll see why in just a second. And we still want to evaluate that from 1 to b. So coming all the way up here, this is the limit as b goes to infinity. Top endpoint, so I'm plugging a b in for the x. So this is b to the 1 minus p, all over 1 minus p, minus, and if I plug 1 into there for x, remember I'm plugging in for x, that's 1 to the 1 minus p all over 1 minus p. All right, now remember this number 1 here that I plugged in there is the exact number 1. So in this case, 1 to any power is actually going to be 1. So that actually is going to simplify nicely. But what happens to this expression here? I'm really looking at the limit as b goes to infinity of b to the 1 minus p. Now, why am I looking at that piece? Well, that's the only piece that's changing, right? Remember, p is a fixed value. That's what we're going to try to figure out what it is. It's just a number. So, what is this value? Well, as b goes to infinity, the question was, for what values does this converge? Which means I want whatever this value is to be a finite value, which means I don't want it to go to infinity. So how can I make sure that this goes to 0, or goes away, basically? Because if I plug infinity right now, if that's a positive exponent, that would be infinity to a positive exponent would be infinity. However, if that exponent happened to be negative, infinity to a negative exponent is 1 over infinity, which is 0. So I want it to be this case so it goes away. So I want this exponent, I need 1 minus p to be less than 0. So in this case, if 1 minus p is less than 0, then what happens to this? Well, that means this piece means we'd have an infinity in the denominator. It would go away. So let me go and write. If 1 minus p is less than 0, then the limit as b goes to infinity of b to the 1 minus p is equal to 0. Then this becomes 0 over 1 minus p minus 1 over 1 minus p, which is negative 1 over 1 minus p. But if you put the negative on the bottom, you get 1 over p minus 1. Now, what do we know about p here? Well, from this statement, this is actually what's going to help us decide this answer. For what values of p will this actually converge? Since we know 1 minus p has to be less than 0 because we need to go on the bottom. This implies, just move the p over, that this will be our answer if p is greater than 1. All right, so let me go back over here. So we actually end up with a very, very interesting result. And we actually answered a lot of the problems that we've done today already. So the question was, if I have the integral from 1 to infinity of x to the p, so 1 over p, over x to the p dx, this is equal to, well, it's equal to 1 over p minus 1 if p is greater than 1, and it's equal to infinity if p is less than or equal to 1. Which means that this thing is going to converge if p is bigger than 1, and it's going to diverge if p is less than 1. Which means if we take a look at one of the integrals we did today, we did from 1 to infinity 1 over x squared, we actually can use this for our answer. All right, our p is 2, p is greater than 1, so our answer is going to be 1 over 2 minus 1, which is 1. And if you remember, that's what we had from earlier today. And you can check this out. We didn't do this integral today. But if I did the integral from 1 to infinity 1 over x cubed, since 3 is greater than 1, I know this answer is going to be 1 over 3 minus 1, which is going to give me 1/2. So without even doing this integral, our result from this gives us the answer to all of those. Same kind of idea. I'm just going to squeeze one right here. If I go 1 to infinity, the integral of 1 over the square root of x. Well, remember, that's 1 over x to the 1/2 power. Since that p is less than 1, this diverges. Or you could say that it equals infinity. Okay, so that's one of our results that we get from this thing. We're going to see this result used later on when we're talking about sequences and series. It's a pretty helpful result that we're going to use. So anything that has a, a bound that's an infinity or a spot to where the function doesn't exist is considered an improper integral. We generally handle improper integrals by taking the improper spot, turning it into a limit, and then evaluating the limit once we actually do the integration.